Proportional odds regression models can be used for a contingency table in a similar manner as a multinomial regression model could be used for a contingency table. And in fact, we can also test for independence with the model. However, the exact test is not the same as what we got with the multinomial regression model. Talk about that shortly. So, what we can do is look at a situation where we have y as our column variable. It is then going to be the response variable for our proportional odds regression model. X is going to be the row variable. That's going to be our explanatory variable for proportional odds regression model. We represent X with I minus 1 indicator variables in the model. So here's the model, what it would look like under the null hypothesis of independence. Notice that there's no X's on the right hand side, so X doesn't have an effect on the response. Then the model under the alternative hypothesis does have X in the model as represented by these corresponding indicator variables. Now we could rewrite our hypotheses or write our hypotheses like this in terms of the model. Now let's compare this to what we had previously with a multinomial regression model when we were testing for independence. The multinomial regression model basically puts no constraints at all on the corresponding probabilities for each category. However, the proportional odds regression model does put constraints on it. So in other words, it's a subset. Its alternative hypothesis model, you could say, is a subset of what would happen under the alternative hypothesis for the multinomial regression model. Some people will say that this is an alternative hypothesis that has some kind of constraints to it, where the probabilities in the alternative hypothesis model for the multinomial regression model have no constraints at all. Now, we talked about this a little bit before when we were talking about hypotheses concerning hypothesis tests concerning proportional odds regression model, and this is the corresponding effect to it. In the end, what this ends up meaning for us is actually our test for independence will have higher power, meaning that you will be able to find indeed that there is dependence more often. You'll have higher power with the proportional odds regression model than with the multinomial regression model, as long as the corresponding, let's say, constraints from the alternative hypothesis model for the proportional odds are actually holding true. We'll see that shortly. Okay, so let's go back to the fiber example. What we have here again is we have a column variable that corresponds to bloating severity. It is actually ordinal. Back before, we had not taken that into account. Now we will. Our explanatory variable, or the row variable for our data set, corresponds to then the type of cracker that's being used in terms of the fiber that's put into it. Here's what our alternative hypothesis model would look like. We have bran, gum, and both as indicator variables corresponding to their levels of the rows of the table. Remember, the other row would be none. In terms of our response, we have levels of none, low, medium, and high ordered in that manner. Let's look at how we can estimate then the corresponding model. Well, first of all, here's levels, just to show you that indeed we do have the levels right. We use the POLR function once again to estimate the proportional odds regression model. Bloat is our response. Fiber is our corresponding explanatory variable. The POLR function automatically creates then the indicator variables for this particular variable. My data is in diet, method equal logistic. Now I do add a weights argument similar to what we had with the multinomial regression model. The reason being is if we actually look at our data, which is already in R here, notice how we have count as a column of our data frame. And so this 5 here represent there were 5 observations that both had gum as the fiber and high as the bloat. And we need to tell R to take that into account. So we estimate the model, we summarize the output. Here's the corresponding model that we get. So for example, here's my beta hats of J0, where beta hat 10 would be 0.0218. Remember, we're going in order here. So 1 is none, 2 is 2 is low, and so on. Now also remember the way that we state our model here is that here's my beta hat 1. But what's actually given here is the negative of it. So that's why we always need to multiply it by -1. And so that's why I have a positive 0.3859 for Bran. To perform the test for independence, we can use a likelihood ratio test. Again, we can use our ANOVA functions for that purpose. I'm going to use the capital ANOVA function here. So here is my -2 log lambda statistic. My p-value is 0.001776. I have a degrees of freedom associated with this test of 3. So comparing to a chi-square 3 distribution, we can see that we have a very low p-value here. So it would be very unlikely to get a test statistic of this large or larger if the null hypothesis of independence was true. So therefore, we conclude dependence in the way that we represent it with our proportional odds regression model. Now compare that to what we got for when we use the multinomial regression model from before. We had a p-value of 0.026. We had a degrees of freedom of 9. In that case, we concluded marginal evidence. Now with the proportional odds regression model, we conclude that there's strong evidence because of how low that p-value is. So this is an example of when that type of dependence exists, we are more likely to find it. We have more power with our test when we use that proportional odds regression model. Another way to think about it is this. So in this particular case, I would use a chi-square 9 distribution. Let's take a look at the critical value that we would use for that test. I would use a critical value of 16.92. Now with using the proportional odds regression model, now I only have a degrees of freedom of 3. Look at that critical value. It's much lower. That's why we are more easily able to find evidence against the null hypothesis with the proportional odds regression model than with the multinomial regression model, as long as the type of dependence that exists is the kind that the proportional odds regression model indicates. Okay, so now that I've rejected the null hypothesis of independence, it's important to go ahead and investigate the type of dependence further. So one could use then odds ratios for that purpose. Please take a look at my book. Please take a look at my corresponding program for how to do that. Okay, so this concludes then this small part of the notes corresponding to using proportional odds regression models in contingency tables.